முடிவு பண்ணியிருக்காங்க. அதனால் மேலும் சில மாணவர்கள் வந்து சேர்ந்து கொள்வார்கள் என்று எதிர்பார்க்கிறோம். உங்களுக்கு வந்து சரியாக கம்யூனிகேஷன் போகலன்னு நினைக்கிறேன். பட் anyhow we will start the program. இன்னைக்கு வந்து முதல்ல ப்ரோக்ராம் முதல்ல தமிழ்த்தாய் வாழ்த்து ஆரம்பிப்பாங்க. தமிழ்த்தாய் வாழ்த்துக்கு பிறகு நம்மளுடைய பாப்புலர் சயின்ஸ் லெக்சர்ஸில் இரண்டு பேராசிரியர்கள் பேசுவார்கள். ஒருவர் ஸ்ரீராம் குமார், உங்களுக்கு முதல்ல தெரிஞ்சிருக்கும், முதல் PSL 1லேயே பேசினார். நானும் அவரோட பேசினேன். அவர் காஸ்மாலஜி பற்றி பேசுவார். அதுக்கு தான் இந்த வருடம் நோபல் பரிசு 2 குரூப்புக்கு கொடுத்துருக்கப்பட்டிருக்கிறது. half the prize, 50% of the prize காஸ்மாலஜியை, பிக் பேங் தியரியை சரியான முறையில் வழிநடத்தி சென்ற பீபிள்ஸ் என்ற நண்பருக்கும், பிசிசிஸ்ட் இயற்பியல் நிபுணருக்கும். பிறகு ரெண்டாவது பிரைஸ் எக்ஸோபிளானட்ஸ். நம்ம முன்னாடியிலேருந்தே பூமியை தவிர வேற இடத்துல லைஃப் இருக்கா, ஏதாவது இடத்துல இருக்க முடியுமா, போய் வாழ முடியுமா என்ற கேள்விகள்லாம் இருக்கு. அந்த மாதிரி ஒரு கேள்விக்கு பதில் சொல்லக்கூடிய அளவுக்கு இப்பொழுது நமக்கு ஒரு தொழில்நுட்ப வளர்ச்சி ஏற்பட்டுள்ளது. அந்த முறையில் பல்வேறு விதமான முன்னேற்றங்களும் ஏற்பட்டுள்ளன. அந்த ரெண்டாவது லெக்சர் அவர் சுஜன் சென்குப்தா, அந்த இதை இந்தியன் இன்ஸ்டியூட் ஆஃப் அஸ்ட்ரோபிசிக்ஸ் அதில் பேராசிரியராக இருக்கிறார். 2 நண்பர்களும் ஆங்கிலத்தில் பேசுவார்கள். ஸ்ரீராமுக்கு கொஞ்சம் தமிழ் தெரியும். நீங்கள் தமிழ் ஏதாவது கேட்டுக்கினாக்கா டெஃபினெட்லி he will be able to respond clearly. But if there is any difficulty, we will help. Many of us are here. We will try to communicate to the speakers so that they are able to answer. We will do something about it. Okay, now we will start with Tamil Thai Vazhthu. நம்முடைய கூட்டம் தொடங்குவதற்கு முன்னர் ஒரு 2 அல்ல 3 நிமிடங்களுக்கு சிபி பாரத், நம்மளுடைய தமிழ்நாடு அறிவியல் இயக்கத்தை பற்றியும் துளிர் ஜந்தர் மந்தர் பத்திரிகைகளை பற்றியும் நாங்கள் செய்து கொண்டிருக்கின்ற வேலைகளையும் இப்பொழுது சொல்லுவார்.
எல்லாருக்கும் வணக்கம். நான் தமிழ்நாடு சயின்ஸ் ஃபாரம்லேருந்து வரேன். தமிழ்நாடு சயின்ஸ் ஃபாரமோடைய ஒரு விங் PSL, பாப்புலர் சயின்ஸ் லெக்சர் group. We are conducting various lectures, the recent trend, emerging trend science and technology. Here we are collecting the TNS of membership and science forum science publications, Tulir and Jantar Mantar subscriptions. If you are eager to get it, please the near registration desk we are collecting. When after the event over, please come and do it. Thank you.
Okay. Hello. Now the first speaker is Dr. Sriram Kumar. He will, of course, it is here, Department of Physics, Indian Institute of Technology. He, very interestingly, as I mentioned, he spoke about Hawking in the first lecture when we were all there. And again, it's about cosmology and Big Bang theory. So the thing is, most interesting thing is our universe, which had started 14 billion years back. We do get information about the whole universe in some interesting way, and we have got fantastic confirmations. It is no longer cosmology. In those days, people will call it as astrology. Now they don't say that. In fact, the developments in measurement, accuracy, and also prediction, theory, everything has developed in the last 40 years. When I was actually started as a student from my period itself. So it is an exciting area of physics. And in India also, we have a lot of work that has been done. And several people who have come here are experts in this. Now I invite Dr. Sriram Kumar to speak the first lecture about formation of structure in the universe. It's a technical way in which it is mentioned, but he's going to explain for what Peebles has been given the Nobel Prize. Okay, thank you.
Thank you, Didier. I had given a talk here, and I'm very glad to be back here talking about cosmology. Check. As Professor Govindarajan mentioned, James Peebles of Princeton University in New Jersey, USA, was awarded 1/2 of the Nobel Prize in Physics for this year for theoretical discoveries in physical cosmology. I should thank the Tamil Nadu Science Forum for giving me an opportunity to give this talk. Cosmology has been, I've always felt that cosmology has not been adequately represented in Chennai. I'm always glad to speak about this topic. What is cosmology? Cosmology is the physics of the universe as a whole. As Professor Govindarajan was mentioning, over the last 100 years, there has been considerable progress in the scientific understanding of cosmology. In particular, over the last 50 years, since the discovery of something called the cosmic microwave background, which will play a very important role in our story, cosmology has emerged as a precision science. The prevailing model of cosmology, again, it was mentioned by Professor Govindarajan, it's called the hot Big Bang model. Professor James Peebles has made many contributions to this model. If you notice, in contrast to other Nobel Prizes, he was not given for a particular discovery. He has made many significant contributions to this, and it is for these theoretical contributions that he has been awarded the Nobel Prize. Evidently, it is very difficult for me to, highlight all contributions of Professor Peebles. So I intend to highlight 3 of the contributions which form a nice narrative for me to tell the story of cosmology, our understanding of the universe as a whole. So this talk does not contain, I think there is just one equation which is easy to understand by all the students. Apart from that, it is aimed at a very generic audience, in particular students. And what I will try to highlight is Professor Peebles' contribution to understand the structure of the universe as a whole. I want you to appreciate that we are not interested in understanding some part of the universe. We see a pattern of the universe as a whole, and we would like to understand how this entire pattern has emerged And that is what Professor Peebles' contributions has been. Evidently, we need to understand what the universe contains before we try to understand this. So I will try to provide you with a glimpse of the universe on the larger scales, which is what cosmology is about. And despite the fact, this universe seems, hardly changing, the universe is indeed changing with time. It is evolving. The universe is in fact expanding. I will try to explain the idea of this expanding universe. It plays a crucial part in our story. Then I will describe the so-called cosmic microwave background. It has played a very significant role. It continues to play a very significant role in our understanding of the evolution of the universe. Then I will highlight one of Professor Peebles' primary contribution. I should mention that Professor Peebles was, and his team were actually looking for this cosmic microwave background as it was discovered, by another team of scientists, two scientists, Penzias and Wilson, not far from where they were working. I will tell you the story as we go along. And then I will explain the need for something called dark matter. One finds that, almost 30% of the universe today constitutes, of 25 to 30%, constitutes something called dark matter, which means it doesn't essentially interact with light. I will try to explain why we believe dark matter exists and what was Peebles' contribution in this direction. And then eventually towards the formation of this structure in the universe. Again, to repeat, we are not interested in understanding, the structure, the star here or a galaxy here, or not even a clusters of galaxies. We are interested in understanding the pattern of the universe as a whole and whether we can understand from basic physics. And I will close with a summary. Let's start with the universe at large. Where do we begin? Again, we are not interested in local objects that would correspond to astrophysics. We are interested in cosmology. So we need to understand what the universe contains. One of the building blocks of the universe is this idea of a galaxy. I'm sure all of you have heard about the fact that we are part of a galaxy called the Milky Way. And the Milky Way, if you are able to, go outside and take a picture of it, it'll look something like this. Very much like the Keralite Appam. There is a bulge in the middle, and all these dots corresponds to stars. And this picture has been taken. We haven't yet reached beyond our galaxy. We have reached hardly beyond our solar system. What has been done is that something called a cosmic background explorer, a satellite, just exposed this infrared camera to all directions of the sky to arrive at this picture. And what we find is that the galaxy is about 45,000 light years across. A light year, I'm sure you all have heard of, is the distance that light travels in a year. You know the speed of light, which is about 3 times 10 power 5 kilometer per second. You know how many seconds make a year, and you can estimate what a light year in terms of the more natural kilometers. Okay, but on the larger scales of the universe, in fact, even light years are not adequate. We need to even talk about larger units. We'll come to that in a matter of minutes. So you are something called 15 kiloparsec. A parsec is about 3 light years. This is an accident. It's a unit which is convenient for us because of the solar system that we are in, or rather specifically the Earth and its orbit around the Sun. And you should remember, a parsec is about 3.26 light years, and kiloparsec is, of course, 10 power 3 parsec, and the size of our galaxy is about 15 kiloparsec. What is its mass? It contains about 10 power 11 stars such as the Sun, but its mass is more than that. This is one of the first hints of something called dark matter. Notice it contains this object here, M, with a circle at the bottom with a dot in the center, refers to the solar mass or the mass of the Sun, which is 2 times 10 power 30 kilogram. And those units, kilograms, are not convenient units. The mass of the galaxy is about 10 power 12 solar masses or so. This is one of the basic building blocks, but this is, too small an object to understand the universe. What do we have around us? Just as, you have a solar system which consists of a star and, some planets around it, you may have heard of clusters of stars, and, there is many large clusters of stars end up forming a galaxy. Well, galaxies themselves form a group. And we are our galaxies form a local group of about 30 galaxies, and this is one of our nearby galaxies. In fact, there are 2 satellite galaxies of our own, but those are very small objects. The nearest big galaxy is something called the Andromeda galaxy. There is another galaxy which is not farther away, which is called the Triangulum galaxy, or M33. We'll come back to this galaxy later in the story. And the distance to the Andromeda galaxy, which is our nearby galaxy, is about 700 kiloparsec, or you're talking about about 2 million light years or so. So there is a large amount of empty space, and there is, these various galaxies are bound due to the gravitational fields of the masses that it contains. So what do you have beyond them? Well, you have varieties of galaxies. You have, this is our own galaxy will look like this. You have some barred spirals, and you have some galaxies which don't have very specific shape. And our universe contains many, many, many such galaxies. And, And then these galaxies themselves, groups of galaxies form a larger group, which is called a cluster of galaxies. And we, the local group, which we are a part of, is part of a larger group of galaxies called the Virgo Cluster, and we are at the end of a Virgo Cluster, and this Virgo Cluster contains about 100 galaxies or so, and we are at the edge, and the Virgo Cluster has a size of about 20 megaparsec. I hope you appreciate the distances we are talking about. Mega is, of course, a million, which is about 10 power 6 parsec. Just to remind you, a parsec is about 3 light years. We are talking about real large distances, and if you look at the sky, there are many, many galaxies. Each extended object here is a galaxy. And there are many such clusters of galaxy. There is famous Coma cluster. There is a Hercules cluster of galaxies, which are, for instance, the Coma clusters contains a very large very large number of galaxies, about 10 power 3 galaxies or so. So what does the universe contains on even larger scales? Well, I'm sorry. Here is, okay, I'm very sorry, it is changing too fast. All right. So here is one of the deepest views of space, which was taken by the Hubble Space Telescope. On the surface of the Earth, the atmosphere limits how well you can resolve the sky, but there is no such limits in the atmosphere, above the atmosphere, which is what Hubble did. There was a telescope which was sent into space, and it captured this image, and it evidently contains a wide array of galaxies. I hope you appreciate that each extended object in this picture is a galaxy in itself. And even this picture doesn't provide you with a complete picture of the universe. So what we need to do is just as you survey your globe, which was done about a few hundred years back, you need to survey our universe. So there was many surveys that were taken out. I will highlight 2 surveys and the results they arrived at. So this is one survey. One such survey. Remember, our galaxy looks like the Keralite Appam. There was an effort to observe the sky to the limits of the telescope that were used to observe north of the galaxy and south of the galaxy. Roughly 1 square degree in the sky north of the galaxy and 1 square degree in the south of the galaxy. And for this reason, it is called the 2DF, or the 2-degree field redshift survey. And actually, the survey extends to about 10 power 5 times more than what is illustrated in the picture. How does the universe look at, on the larger scales? Well, it looks something like this. So these are the 2 different directions. These cones represent the 2 different directions of the sky, north and south of the galaxy. And I hope you appreciate that each dot here in this picture represents a galaxy. So what do you see? You see a pattern of, structure in the universe. This is what I mean by structure on the larger scales. And our goal is to essentially understand how this all arose. What is the physics? How did eventually these galaxies form, or clusters of galaxies this form? And there has been this, survey is a couple of decades old. There has been a more systematic survey, something called the Slow and Digital Sky Survey. It has produced a nice video of how the universe looks on the larger scales, I'm just going to play that video for you. I'm sorry. Okay, it consists of one of the most ambitious and influential surveys in the history of astronomy, and it operated for close to 80 years or so, and it observed many, many galaxies and many other objects, compact objects called quasars. I'm just going to play a movie for you which illustrates how the universe looks on the larger scales. So what do we have? We have the Milky Way here. What you should notice is that there will be two yellow grids that will emerge, one at a distance of 2 million light years, roughly the distance to the Andromeda galaxy, okay, and another at 1 billion light years. And we will see this is about 1 million light years, not 1 million light years. The Andromeda galaxy is still not in. The Andromeda galaxy will start coming in very soon. It's largely empty space. And as you go further and further, so you have the Andromeda coming in. So we are at a radius of about 2 million light years. The speed of the movie, doesn't mean anything, all right? And as we go on and, at larger and larger scales, you get to see many, many more galaxies, as will become evident very soon. And what the Slow and Digital Sky survey did was that, the 2DF field observed just one cone, and one cone in the south of the galaxy. Slow and Digital Sky survey surveyed in 6, 7 different directions in the sky. And this is what you see. Okay? And the different directions will become evident. They will rotate this picture to illustrate the different directions in which it has been observed. Don't worry about the different colors. What I want you to appreciate, each dot here represents a galaxy, and this is the pattern of the universe as a whole. There are few different directions in the sky which the survey has observed, and it has this catalog of galaxies, and it is able to map the universe to a good extent, of course limited by its resolution limited by the resolution of the telescopes. And the goal is essentially to understand this pattern that you see. There is something else that will emerge in a matter of seconds. Sorry?
That pattern and constraint imposed by the instruments, or is it the way that they...
Okay, so there is a constraint imposed by the instrument in terms of the resolution. So at the edges, I'll just complete the story and come to you. So what happens, you see a pattern beyond here in terms of blue, yellow and red dots. That will play an important part in our story. We'll come to that in a matter of minutes. And in response to your question, there is a limitation. You can see that evidently there is a limit to which it is observed, and there are less number of galaxies toward the edge rather than in the middle, and that is imposed by the limitations of the telescope, where it is able to observe the brighter ones and unable to observe the less brighter ones. I'm sorry. I hope that answers your question. Okay, so this is the pattern of the universe. What happened to the universe? Is it static? No, it is evolving. And how do we understand that? In fact, it is expanding. How do we understand that? Well, all we need to do is look at the spectra of galaxies. You have light coming from the galaxies. You just need to send it through a prism and look at the spectrum, and it reveals something interesting. So, what is a spectrum? I'm sure you have all heard of the electromagnetic spectrum. So this is a typical continuous spectrum. If a body contains many elements and you heat it up, this is the kind of spectrum that you will obtain. If you have specific elements in that body that you are heating up, then it will evidently emit only at discrete wavelengths corresponding to the atom that constitute the element. Or you can have another situation. You have an electromagnetic source far away, light source far away, and there is cool gas in between, and you will see the absorption lines. if you have heard of the Fraunhofer lines corresponding to the spectra in the sun, you will have corresponding spectral lines which will reflect the elements that constitute the gas. How do the spectra of galaxies look? The galaxies contain very many elements. So this is a typical spectra of some of the galaxies. And what they will have is that they will have strong emission lines corresponding to certain transitions of elements, and a trained astronomer will be able to pick up what these lines correspond to easily, and there will be a variety of absorption lines. Now, what I can do is that I can compare the spectra from the stars in our galaxy to the spectra of faraway galaxies. What do you find? You find that they redshift. What does it mean? If the source is receding, right? If this is the spectrum in the source's frame, I have two sources, one which is in my frame, another which is being taken away by my friend in a motorbike, okay? Then what do you see? This is the spectrum that I obtain from the light source in my frame. But if I compare that spectrum with the spectrum of the light source is being taken away in the motorbike by my friend, then what you will find is that the spectrum will be shifted to the red end of the spectrum. Okay? And you can attribute something called a redshift, which essentially reflects the change in the wavelength to the original wavelength. And now you can ask, what is that galaxies display? What one finds is that the galaxies exhibit something called a redshift. All galaxies, or rather most galaxies to be precise, exhibit something called redshift. What happens? This is, a spectrum of, say, a star or a collection of stars in our galaxy. Okay? And I can compare that spectrum with the spectrum of a galaxy which is some distance away, and another galaxy which is even farther away, and a galaxy which is, say, even further away than the previous two. Then what one finds is that, these blue lines indicate a particular transition. You can pick up any transition you like, okay? And you look at a particular transition, like the strong emission line that you observe, what you find is that this red horizontal arrow indicates the extent to which that particular line has been shifted towards the red end of the spectrum as compared to the spectrum from a star in our galaxy. So what you find is that, galaxies exhibit redshift, systematic redshift. And these are actually spectra of 4 different galaxies from the 2DF redshift survey that I had discussed about earlier. What does this indicate? Well, what one also finds is the following. There is a specific relationship between velocity and the distance of galaxies. The velocity is easy to understand. We had seen this, I'm sorry, this seems very sensitive. We had seen this relation, and the extent to which the wavelength shifts depends evidently on the velocity of the motorbike which is taking away my friend. And therefore, I can determine the velocity once I know the extent to which a particular, line has shifted to the red end of the spectrum. I can determine its velocity using this redshift z. And I can determine the distance to the galaxy. I have said it very easily. One of the most complicated things to do in cosmology is measuring the distance to a galaxy. It's very non-trivial. If you are interested, you can speak to me later, but for want of time, I will proceed with my story. So you determine the distance to the galaxy, and you... Okay, you determine the redshift, distance to the galaxy. What has been plotted is velocity obtained from the redshift, okay, and the distance to the galaxy. What one finds is that the larger the distance to the galaxy, the more faster it seems to be running away from us. Okay, this is a somewhat old picture. In fact, it's almost 100 years old, and this linear relationship between velocity and distance is something called the Hubble's law, and it was discovered by Hubble in the middle of 1920s. And this is a more modern diagram. Well, it's still 20 years old, and what it tells you is that two galaxies, that are separated by a distance of 1 megaparsec are moving away from each other at a speed of about 72 kilometers per second. What it implies is the following. Think of the picture, okay? There are many galaxies, and the farther the galaxy, the faster it is moving away. And what it means is that two galaxies, which are separated by 1 megaparsec, this guy sees this galaxy moving away at a speed of 72 kilometers per second away from him, and this person, sees this galaxy moving away from him at the same speed, which essentially implies that the universe is expanding. Okay? There are important points to understand, conceptually what it means expansion of the universe. I will try to clarify in my next slide. The first thing is that the universe is expanding, and the second thing is, it implies that as you run this movie backward, think of all these guys that are moving away, galaxies. If you run this movie backward, it seems to suggest they were all on top of each other at some time early in the past. And this particular notion of time, where all the galaxies seem to have been on top of each other, is something that is referred to as the Big Bang. And Professor Govindarajan mentioned a certain number, namely the age of the universe. He said it's about 14 billion years old, and this is easy to understand from this speed. Notice it is kilometer per second per megaparsec, okay, which is essentially the slope of this curve, and this, has units of 1 over time. I would, if you're a student interested in carrying out this calculation, I would urge you to invert this and estimate a time scale, and that time scale you will find that will be of the order of 14 billion years or so that Professor Govindarajan mentioned. And another point to highlight is that, notice, this red box here, is the original Hubble plot. This is a more modern plot. In fact, there are modern plots which has been able to obtain this, Hubble diagram for even larger distances. There are a couple of points I need to clarify. How do you visualize this expansion of the universe? And what is this redshift? Now, I have given this idea that these galaxies are moving away, and because it is moving with a certain velocity, there is a Doppler effect, which is what we see as redshift of galaxies. This actually is an incorrect picture. On these larger scales in the universe, the Newtonian gravity you would have learnt at school is inadequate to explain the physics of the universe on these scales. At greater strengths and larger scales, Newtonian gravity fails. And it has to be replaced by a superior theory known as Einstein's general theory of relativity. And it is in this context you have to understand this idea of redshift. In Einstein's relativity, the universe, is described by, by something, notion of space and time, space-time, okay? And the way you should imagine is you can think of the universe as the surface of a balloon, okay? And as you blow the balloon expands. What it means is that on the surface of the balloon, if you put two dots, like these yellow patches, the distance between them increases with time. And what you can show is that if you have such a geometry, expanding geometry, if you leave a photon in this geometry, it will lose energy. And that is what you see as redshift, and it is actually not a Doppler effect. It is convenient for me to introduce the idea, but it is something called a cosmological redshift. You should understand, if I leave an object in this universe, because of the fact that the universe is expanding, it will lose energy, whether it is a photon or even, particle with some mass. So, the universe contains many objects. It is expanding. It evidently contains matter. Does it contain anything else? Evidently, it contains radiation. You see light from the stars. That is how you actually observe the galaxies. Okay? One of the important things that we recognized over the last 50 years, that, the dominant form of radiation in the universe is not the light from the stars. We find that we are bathed in a thermal distribution of radiation, and this is known as the cosmic microwave background. And this is where, the Peebles contributions and the Peebles story comes in. As I mentioned, the idea of the expanding universe, general relativity, was formulated in 1915. In the mid-1920s, we have begun to realize that the universe is expanding. And between 1920 and 1950, 1960, there was a lot of effort in trying to understand what happened in the early universe if the universe is expanding. And it was recognized that the early universe could have been hot, okay, and there would have been radiation, and this radiation should be seen in the sky. And in fact, in the middle of 1960s, Peebles and his group at Princeton University, there was a person by name Didier who was good at designing instruments, and someone by name Wilkinson, whom we will encounter again later in the story, were trying to design a radiometer, something to observe, but this radiation in the sky. There are reasons to believe that this radiation will be thermal, just as the spectrum, as you heat a body, okay, will be thermal in nature, but what was not very well known was the temperature of this radiation. It was estimated to be of the order of 5 to 10 degrees, and in fact, Peebles was the theoretician who was helping calculate these quantities, and there were these experimenters at, Princeton University who were trying to, actually measure this radiation. Meanwhile, what happened was as follows. There were two people, Penzias and Wilson, who were at Bell Labs, and they happened to have an antenna, okay, which, measures at this microwave, which is sensitive to these microwave frequencies. And what they were doing is that they were just trying to measure the radiation from the galaxy, okay. I showed you a picture of a galaxy which looked like that Keralite Appam. Think of the galaxy at the center and the universe around it, okay, and the galaxy lies here. And they were trying to measure the radiation from the galaxy in certain region of the electromagnetic spectrum. And what they found was that, there was a noise which was refusing to go away. Then they cleaned up the apparatus, okay. In fact, there was a famous story where there were two doves there which were repeatedly coating the apparatus with a dielectric substance, okay. They were pooping on the apparatus very regularly, and they cleaned it up and tried to measure this radiation again, and they found that there was this noise which was refusing to go away. And they had no clue what this was about. And just a few kilometers away, there was people, these are the two papers in the Astrophysical Journal. There were people, Didier, Peebles, Roll, and Wilkinson, were actually trying to construct an apparatus to measure exactly this radiation. And, there was a phone call. There is a famous story of a phone call from Penzias and Wilson to one of members of the group, I believe Didier, and, who said that we have been scooped. And in fact, Penzias and Wilson, for their discovery, won the Nobel Prize in 1978, and Peebles won this year. Okay? So this is, actually, I just caught a glimpse. This is the paper by Penzias and Wilson, and this is a paper by these four people at Princeton University, which explains why there should be a cosmic black body radiation or thermal radiation which has been observed by Penzias and Wilson. So this is the sky. I'm sorry, I should go back. So this is the sky, the CMB sky. Okay, we will begin to see more patterns in this, and they will form an important part in our story. And this temperature, as I will describe, is about 3 Kelvin or so. So this temperature comes from all directions in the sky. Okay, and this is the paper I had already mentioned. And so what Penzias and this is the black body spectrum at a temperature of about 2.7 Kelvin or so. And this is what Penzias and Wilson observed. And what has since happened? Well, we have okay. This is a more modern version of that spectrum where people have observed a wide range of wavelengths. Okay, this is the spectrum of background radiation in all different regions of the electromagnetic spectrum, ranging from, very small wavelengths to very large wavelengths here. And notice it peaks in something called the microwave region of the spectrum. And as I will describe, it is cosmic in origin. It's everywhere, which means it's a part of the universe. It was not created by a small event here or there in the universe. And it is for that reason, it's called the cosmic background. it peaks in the microwave region of the electromagnetic spectrum, and for this reason, it's called the cosmic microwave background. And this, this is where that spectrum is, and this has been measured, very exquisitely by a satellite called Kobe. All right, we will again encounter the satellite later, and this is the actual thermal spectrum. The dots with error bars are the observations or the measurements, and this curve corresponds to this 2.725 Kelvin. Okay, and what I should emphasize is these error bars have been enlarged by 400 times so that they are visible in this graph. In other words, it is one of the most perfect blackbody spectrum you will encounter. So what does this imply? This implies that the universe, apart from matter, it also contains radiation that was clear from light from the stars and galaxies, etc. But those don't constitute the dominant form of radiation. The dominant form of radiation is this so-called cosmic microwave background. And if you use general relativity and the fact that universe is expanding, what one can show is the following, that the universe began in a hot, dense state. If you are a young student, okay, who watches American sitcoms, you may know this guy called Sheldon, who is this theoretical physicist who appears in this sitcom called The Big Bang Theory, and this is the first screen, this is the first screen that appears as the sitcom starts, and it starts with the statement, our universe was in a hot, dense state. So you have matter, you have radiation, and using general relativity, you can immediately argue that very early in the universe started in a hot, dense state. It cooled down as it expanded, and this is actually the origin of the CMB. And let me quickly explain what the CMB is. So what you have is as follows. What you have is as follows. This bath here, yellow bath, corresponds to the photons in the universe. Okay? And these are matter. This large ball are protons. These small balls are electrons. Very early in the universe was hot, okay? And the photons had a large amount of energy. As a result, if an electron tries to combine with a proton and form an atom, this photon will knock off the electron and the electrons will remain free. But as the universe cools, what happens is that atoms form. Here is a hydrogen atom. Here is a helium atom with 2 neutrons and 2 protons. The big green balls are neutrons, and the red ones, as I already mentioned, are protons, and it forms a helium atom. And notice what happens is that these, photons start streaming freely. This is the early part of the universe, this is the late part of the universe, and the photons start streaming freely, and in fact, they travel from that time to us virtually uninterrupted, very much in a manner. What you see is that, if you have a cloud here, what happens is that there are photons which have a very small mean free path. They are constantly scattered by the water molecules in the crowd, but once they cross this part, it travels to you freely, and that is what these photons do. They have a very short mean free path very early in the universe, but once the temperature cools down to a certain extent, by a certain extent, the photons start traveling freely and reach you, which is what you observe as the CMB. And you can, in other words, you see the CMB in all directions in the sky. Just as the surface of the Earth can be, projected on this ellipse, you can project the entire sky on this ellipse, and we will see this projection in the CMB. This is the projection I had shown earlier, if you recall, and that earlier projection, as observed by Penzias and Wilson, had no pattern at all. But more modern measurements are beginning to see patterns, and this takes us to the second part of the story. And these are, what I find is that the temperature of the CMB, I said it's about 2.725 Kelvin today. And it is largely the same until the third or the fourth decimal place. But if you go to the fifth decimal place, what you see is that beginning to see deviations in temperature. In other words, the temperature in this direction of the sky, if it is 2.72543, here it could be 2.72548, for instance. There are 1 part in 10 power 5 deviations, and in fact it is these deviations which are responsible for all the structures in the universe, and therefore you and me. Okay, so the second part of the story goes to the idea of dark matter. Why do we need dark matter? It's easy to understand. We have already seen, it's very sensitive. We have already seen how there exist spiral galaxies. In fact, we had seen this triangulum galaxy earlier in the slide. This is this galaxy. Okay, this is the galaxy on the right hand side here. Okay, now what you try to do is that this is the galaxy that has been displayed as the background. You try to measure, I can easily measure using redshift of the spectra, as I've already indicated. You try to measure the velocity with which the galaxy is rotating from the center of the galaxy to farther away. Now, if there was only matter present, the visible matter that is present in the galaxy and nothing else is present, what you find is that the velocity, on these scales, the Newtonian physics is adequate to describe the dynamics, and we can use Newtonian physics, and this is actually the famous Keplerian curve. And if you think that there was matter only here, then what you find is that the galaxy, velocity should have dropped by like this. But what you actually find is the velocity keeps increasing with distance from the center of the galaxy. What it means is that there should be matter present beyond this visible region. And the modern view is that this, where Peebles contributed greatly, is to understand that the galaxy is embedded in a halo of dark matter, and this is what this paper highlights. Okay, this is a paper by Oestreicher and Peebles, which was written in the mid-70s, which indicates the fact that the galaxies are embedded in a larger halo of cold, what is referred to as cold dark matter. It's called dark matter because it doesn't interact with light, and therefore you can't see it directly. Okay, and what you find is that if you want to explain these rotation curves, you need to have this dark matter present, which extends to greater distances than where you see the visible matter. In other words, there is a huge dark matter halo which surrounds these galaxies. The dark matter creates a potential. You know that matter creates a gravitational fields. It creates a gravitational potential which others fall, and that is what cold dark matter does. And there are various evidences for dark matter. This is, something called gravitational lensing. In the modern language, what you have is that you have a foreground galaxy, which is a large, luminous, red galaxy, which has a huge mass. And there is a blue galaxy in the background. What has happened is that gravity bends light. And therefore, you have a faraway galaxy, you have a huge mass in the middle, just like a lens. What it does is that it takes lights from different directions and converges towards me. And that is what you see as this famous Einstein ring. And it again indicates the presence of dark matter much beyond the extent of the visible region of this intervening galaxy. And there is yet another observation. I will try, for want of time, I will not spend on this. Okay? It's a famous bullet cluster. If you're interested, I can speak to you later. Now, these are local effects. What is the cosmological evidence for dark matter? Well, this is where Peebles contributed as well. I mentioned about the CMB. I also indicated that the CMB has anisotropies. To a first, third, or fourth decimal place, the temperature of the CMB is the same in all directions of the sky. But you measure at the fifth decimal place, there are deviations in the temperature, as I had indicated, to 1 part in 10 power 5 or so. Now, the question is, how did these, deviations, anisotropies arise, and what is the cause of this? And this is where Peebles' third contribution came in, okay? And he was able to explain as to how dark matter is essential to understand these patterns. This is a more modern version of this CMB sky. This was by Kobe, which I had mentioned. And if you observe the sky with greater and greater resolution, you begin to see these patterns in the CMB sky. And this is the full sky, as observed by WMAP. In fact, the WMAP is named after, W is named after Wilkinson, who was one of the 4 people who were trying to observe as Penzias and Wilson scooped them. Okay, and there has been exquisite measurement of these anisotropies over the last decade or so by an instrument called Planck, which has observed the CMB sky from, in an orbit beyond, from the sky. Okay, and what one finds is that you need this dark matter in order to explain this pattern of anisotropies. The last part is what we had started with. I had shown this picture of the universe as a whole. Can we understand this? Unfortunately, what happens is that it is very complicated dynamics, because you are talking about millions and millions of galaxies whose dynamics you need to evolve. And what happens is that it turns out to be a very nonlinear system. Linear systems are easy to solve. The universe in this regime where they are interacting strongly is a nonlinear system. So therefore, it is difficult to solve using simple tools in mathematics. You have to turn to a computer to simulate whether, how these particles evolve, how these galaxies evolve through the interactions, and that has been done. And what I will show, I will conclude in the next 5 minutes or so. What I will try to show is these results from these computer simulations, and what I will try to impress upon you is the results of these computer simulations match the pattern of the sky with these dots of galaxies that I had shown earlier. So I'll just skip this slide. So what I'm going to show is the following. So think of this pattern, okay? Okay, I'm just going to, bear with me. So think of this pattern. It's a largely smooth distribution of dots, okay? But evidently, there has been some tiny deviations from a very smooth distribution, okay? Think of the universe where there were masses present, dots present, which represent maybe a small collection of objects, okay? And there are some, deviations from smoothness. What one finds is that if there are deviations from smoothness, gravity will take over. If you have a distribution of masses, even if there is a smallest of deviation from smoothness, what will happen is that where this deviation exists, the masses will accumulate and will start forming larger and larger structures. This is how actually the structure we see around in the universe has been created, and the large-scale structure that I mentioned about. And this set of slides that I'm going to show you will illustrate if I start with small disturbances like this, and I allow them to evolve through gravitational interactions, how they will evolve. Sorry. So as time evolves, what you see is that the masses, accumulate and they form this pattern, which are very similar. This, for instance, could be a large collection of galaxies. Okay, this is a glimpse of what can happen. There has been a major computer simulation, which I will try to play in a matter of minutes. Okay, so there was a huge run, okay, computer with about a 10 billion particles, okay, over a large region of the universe, and this is what the result is. So you can see this pattern. You're talking about, this is the entire universe as a whole. This is the result of a computer simulation which ran for, in a very large computer for almost a month or so. And you're talking about something like 500 megaparsec. What they're trying to do is that this is the result of the simulation. They're trying to zoom in and try to give you a picture of what has happened. Now you can begin to see what that there is a gravitational field that is formed originally due to dark matter that I had mentioned about in the few minutes back. And then visible matter falls in. As visible matter falls in, it heats up and it starts emitting light. And this is the kind of pattern that you saw in that survey that I had seen earlier. And Peebles was one of the earliest people to actually run computer simulations to understand the formation of structures in the universe. As I mentioned, he also played a significant role in helping us understand the role of dark matter in the formation of structure. So they are now zooming out to the eventual result that you have. And this pattern that you see is supposed to look very similar to the pattern of the survey that I had shown earlier. So I'm almost towards the end of my talk, so I'll just quickly summarize. So this is the view of the universe that we have currently. The universe began with a Big Bang, and it was a very hot, short phase. And this is the pattern of the anisotropies in the CMB that I talked about. Okay? And there is something called the dark ages. What has happened is that the structure is forming, but stars haven't yet formed to emit light. So there are dark ages here, which people are beginning to understand today. As time went on, the first stars formed, they started emitting light, and eventually galaxies formed. And Peebles contributed, as I already described, to the discovery of the cosmic microwave background radiation. I do not know what could have happened if Penzias and Wilson did not have someone to explain to them that they have seen this cosmic microwave background radiation. There have been history of people observing the CMB through other means much prior to Penzias and Wilson. So Peebles played a significant role. As I mentioned, he also played a role in understanding the structures of galaxies and the role played by cold dark matter in forming these galaxies. And he has actually played a significant role in our understanding of the structure that we see around us today, okay, over these distances. In fact, if you notice this tube, it reflects how the universe expands. The universe expands through a very large period here, and then it slows down, and then you can see that the universe begins to expand through an accelerated fashion. It is driven by something called dark energy, and Peebles has played a role in our understanding of dark energy as well. He has models, which are not necessarily supported by data, okay? And, but for want of time, I couldn't spend time on those aspects. So let me summarize. Peebles has contributed to arrive at this standard model of cosmology. What it says is that the universe is homogeneous and isotropic. What it means is that we saw that there were patterns of galaxies, but if you look at a sufficiently large region of the sky, and if you take a sphere of the order of, with a radius of the order of 100 megaparsec or so, what one finds is that independent of where you place the sphere, the amount of matter in the universe is roughly the same. Okay? Another point, baryons, that is what you and me are made of, actually contribute to less than 5% of the total density of the universe. And I mentioned about 25% of the universe today constitutes something called dark matter. And I highlighted Peebles' role in our understanding of cold dark matter. What I could not spend time on is, quantum fluctuations. This is what I had talked about in my first talk in the Tamil Nadu Science Forum, how quantum fluctuations are what created those anisotropies in the CMB. Okay? And these anisotropies in the CMB, which, eventually turned due to gravitational instability. So I showed you this small pattern with small disturbances in the pattern, in this distribution of matter. And those small disturbances are adequate to eventually, through gravitational instability, your good old gravitational force, to lead to the structures, this pattern of structures that we see around us today. With those remarks, I'll stop here and thank you for your attention.
Thank you, Sriram. Please take a seat. We'll go for the questions after the second talk. Sriram gave a fantastic talk on how the universe originated 14 billion years back. And he made it very clear what we know as we do experiments here is only 5% of the matter. Protons, neutrons and other things, stars which we see, all the things, you add up all of them which you see, okay, is only 5%. Another 25%, they are all with us. Here, everywhere, they are dark matter. We don't even know. They don't interact with us. And it is responsible for the galaxies, the galaxy formation. Without that, we can't understand, unlike the Keplerian law, where the farther you go, the velocity of the planets decrease. But unfortunately, in the galaxies, the farther you go, they don't decrease. The star's velocity don't decrease. So the Kepler's laws cannot be applied in this thing. And that is what forced people to think that there is something more there everywhere which is not interacting with us. And the most interesting thing is the gravity is among the first force which was discovered, is also the most awe-inspiring, extraordinary. From Newton and then Einstein, the space-time, and then you think of that as kind of a rubber sheet and then there is some bulge somewhere. That kind of a thing which structures which are coming in space-time, which are making it very interesting. So now we are going to have Dr. Sujan Sengupta from Indian Institute of Astrophysics. He will talk to us about the exoplanets. So we were always wondering, is there life beyond Earth?
Yes.
Okay. Is there life beyond Earth? Wherever can we see? Or even we try to send signal, or they will send signal to us. In fact, he talked to us yesterday in our institute, search for unintelligent life. He is actually, it looks like he is worried if the life is very intelligent, more than us, they will kill us. So it's better that it be unintelligent so that we can kill them. So now Dr. Sujan Sengupta, he has a book also. He will probably explain that, mention it towards the end. And people will find this talk very interesting. And the origin of the search for exoplanets, you will understand, as he mentions, started here in Madras. Okay? Thank you.
Thank you, Professor Govindaraju, for a nice introduction. Good afternoon, everybody. And it's not only a pleasure, but I feel honored to be here. I feel honored to be here among you to give my lecture. Now, I think most of you or all of you have read science fiction, where you have come through alien life, the intelligent life, either we are going or invading, and you have definitely watched the movies like E.T., Interstellar, Avatar, etc., etc. Today I am going to tell you the systematic scientific search for life. Now, why do we need to search for exoplanet or exoworld, or why do we need to search for life? That is because we humans are this is not here. Let's see why. Yeah. So that is because we are curious to know if anybody out there, or we are the lonely play, we are the only life in this earth, or if life is a common phenomenon in the. Now, when usually you talk about search for life, we have the concept that about intelligent life, all the science fiction books and everything that is concerned about intelligent life. What is this intelligent life? So we all human beings are considered to be intelligent. You may say that biologists also say that humans are intelligent, or the monkeys are intelligent, even the octopus, they are also intelligent. Environmentalists can also tell that the ants are also intelligent. But we cannot detect intelligent species outside the solar system unless and until it can generate electromagnetic wave artificially, can transmit it or can receive it. In that way, we acquire this technology of generating or receiving electromagnetic wave just 150 years ago. So our signal has passed only 150 light years distance. Now, if we want to detect life from the very corner of of our galaxy, so that will be another 25,000 light year. That means that civilization has to be 25,000 year old civilization. So today I am not going to tell you about the search for intelligent life, but rather I am going to tell you the search for life, whatever kind, intelligent or unintelligent, nascent, bacteria, plants, everything. This is the problem, not. Now we know one planet very well. That is our Mother Earth. That is our world. And as soon as the old Aristotelian concept of a geocentric Earth was abandoned, this concept was there. Earth was in the center, and Copernicus' theory of geocentric Earth was established. Where we know that the Earth is orbiting around the Sun, along with sibling the other 7 planets. The speculation, some of the scholars have started thinking that if that is the case, then all the billions and millions of lights in the night sky are also Sun, and in that case, they may also have planets. If that is the case, then there may be some planets which are very similar to our Earth. And if that is the case, if Earth-like planets exist elsewhere, then there could be life. So that life may originated from such type of consideration. But then the people, many people with whatever technology they have, the telescope they have, they searching for planet. It was not so easy thing, and nobody could report any or any evidences. Finally, in 1885, an astronomer from very city, in one observatory called Madras Observatory, for the first time reported in a journal called Monthly Notice of Royal Astronomical Society, the first of a planet outside a solar system. This Madras Observatory was established in 1786 by the British East India Company. Before that, it was in Madras Egmore as a private observatory. The British East India Company took up it to do the star. And in 1800, next, Captain William Stephen Jacob was the director from 1848 to 1959. By using a small telescope, 6-inch telescope and 8-inch telescope, he monitored the movement, the position, from the position of 2 stars in a binary system called 70 OPOC. He detected the movement of the stars, that these 2 stars are not following exactly the Kepler's law. So, in that, he suggested if there is a planetary mass object as a third object orbiting any of the stars or system, then that could explain it. Immediately after the was published in 1955, observer from Chicago University also supported his claim. For 50 years, nobody challenged this thing, but after the telescope has improved, found that this was actually a false alarm. He made a mistake because he didn't consider much about the atmospheric effect. But at that time, this thought that a planet can explain the motion of a binary star was far, far ahead of that time. Then subsequently, and observations for detection continued. Now, this Madras Observatory, what happened there? In 1893, the Madras got meaning. And then the British thought that it is not worth of monitoring the stars, rather it is worth to study the sun, because that causes the famine. So they wanted to shift this observatory to Kodaikanal Observatory, and then it has gone, the next one. And so this Madras Observatory was shifted to Kodaikanal, that is also in Tamil Nadu, and it becomes completely a center for the research of 1971, it came under Central Government Department of Science and Technology under the Indian Institute of Astrophysics. At the same time, another observatory which can study the stars, galaxies and other things came out in another part of Tamil Nadu, and that is in Kavalur, that is also in Tamil Nadu. Here you can see that this is so far the Asia's largest optical observatory. It has still Asia's largest optical telescope, a 2.4 meter optical telescope called Vainu telescope. There are many other telescopes, and Captain Jacob started from Madras Observatory. We people, they are with the astronomer, I and my group, they continue by using this telescope for new world, the search for new exoplanet. In any case, after that, after this motivated work by Captain Jacob, many people attempted, but all were turned to be false alarm. Finally, in 1995, this gentleman, Michel and his PhD student Didier reported the first discovery of a planet around a type of star. This paper in the October of 1995, immediately within 1 month, a group led by Geoffrey Marche confirmed that what they have got is correct. They have also got the same result, giving it the status of the first confirmed planet around a solar type of star, so outside our solar system, and awarded after 25 years the Nobel Prize. So here is the star. You can see that star that planet he has discovered around the star in the Pegasus constellation. But clearly, if you see that even through a very large telescope, the star will appear like a point object. The planets, they don't emit, they don't have their own emission, so they the starlight, and they are hidden by the intense light of the star. So it is not possible to detect such type of planets outside the solar system by direct method. Michel and Didier did it, an indirect method. And what is that method? So now that is called a Doppler radial velocity method, which was proposed in 1952. Now, if you have a binary star, they don't rotate around anybody's center. Rather, they rotate around a common point, which is called the pericenter. Now, if the mass of, if one of this component, one of this pericenter moves towards the heavier star. So now what will be happen if planet orbits a star? This pericenter will go inside the star, but not exactly the center of the star. As the star will ubul. It will go towards you, or it will go away from you, or it will just ubul in which direction watching it. So what they do, that the astronomer passes the starlight through a prism, is called, the instrument is called the spectrograph. I think the previous speaker has nicely explained this spectrum. So when you pass to the spectrum, the starlight through a spectrograph, you notice certain lines, vertical dark line, which are the signature of the matter present in the outer layer of the star. The star is absorbed by this material, and that causes this line, and each line can be distinguishable by their position in the entire spectrum. Now, if the star moves towards you or away from you, that causes the shift wavelength. So, already it is discussed in the last lecture that there is a shift when it moves towards the blue, when it moves you, that the source of the star, and it is at the rest if there is no movement, and it moves towards away towards the red side if it is away from you. This is called the Doppler redshift or Doppler blue. Doppler actually it for sound wave, but then later on it was found that this is applicable for the light wave also. And this Doppler shift plays a very important role in astronomy. So now what's the situation here when planet orbits a star? So here it moves around the star. The star wobbles. As a result, the line that shifts from blue to red to blue from the center, and this happens periodically. If you convert it into the velocity, you can get the motion of the star. So this is the radial velocity method. This method was followed in the beginning and by the Michel and Didier. Actually, our Jupiter, it emits a radial velocity to the sun about 12.7 meters per second. Our Earth also imparts a radial velocity to the sun, but that is only 10 centimeters per second. Now, at the time this method was proposed, the existing instrument could detect only if the radial velocity of the star was 1 kilometer per second. Now, Michel and Didier, they developed a sophisticated instrument that is called LOD, which could detect radial velocity of the star as small as 7 meters per second, because they thought that the planets will be in Jupiter position, or then Jupiter size of planet or Jupiter position can be detected. And then targeted list of stars. So this is Didier, and then fortunately for them, they found out the radial velocity of the star, 15 Pegasi, as 56, about 56 meters per second. And this was, when transferred into the velocity, they get a very perfect periodic movement in the star's radial velocity. And that confirms the presence of the planet, the first planet around the solar system, and it was named as 51 Pegasi e. Now, for the next 5 years, quite a few groups developed sophisticated instrument, the spectrograph, and tried to detect many planets, and many planets was discovered through this method. At about 100 or 200 planets has been discovered by using this radial velocity method. But then in 1999, planet was discovered by using another method, and that is called the transit method. So just on 11th November, you heard, or some of you might have seen the video NASA that Mercury is transiting across the sun. So this photo was taken in IIA's setup, transit of Venus, in June 6, 2012. You can see that the shadow of Venus is falling over the disk of the sun. And this makes tiny change in the brightness of the star. If the planet is much near to the star, if it is much larger, then detectable amount of drop or reduction or decrease in the brightness of the star. And that principle is used by the astronomer to detect large exoplanets which are very near to the star. So when the planet transits across the star, there is a systematic drop in its the brightness of the star, and this becomes perfectly periodic. So in also we use this method, although this method is simple in principle, but it's a very tedious method because you have to reduce the data, you have to remove the atmospheric effect, everything, and then you have to model and fit it. This method became so popular that it prompted European Southern Observatory, European Space Agency to launch a dedicated spacecraft, Queloz, in 2006. Subsequently, in 2019, NASA sent a space probe, dedicated space probe that is called Kepler. So as soon as Kepler was launched, hundreds of thousands of stars having planet has been discovered, and our entire concept of the planets, planetary properties, planetary formation got into change. And before that, even the discovery of 100 planets, their was so different that prompted the Parliament of Astronomers, that is called the International Astronomical Union, to sit down, to vote, and define the definition of the planet, the properties of planet. As a consequence, Pluto lost its status of being a planet. I think many of you know that story. So before Kepler was launched, we knew only 8 planets, and the largest planet and the heaviest planet was Jupiter, which were far away from the Sun, the rocky planet, which were very near to the Sun. But once Kepler discovered hundreds and thousands of planets, we saw that planets of larger than Jupiter and be 10 times more heavier than Jupiter exist and operating around other stars. And also they are so near that they are very hot. Even they are so hot, then iron or gold can also melt in their atmosphere. There are many other kind of planet which has a extensive atmosphere, and there is a small rocky core. These are called mini Neptunian, not present in our solar system. So maybe this is the transition from a rocky planet and a planet like Jupiter. So the diversity in the planets and their properties has gone beyond our imagination. Now I will show you a few outstanding we have discovered. The first one, here you see a planet is discovered, is orbiting 2 stars. This is called Circumbinary Planets. In fact, our nearest star, Proxima Centauri, it has a planet. Now, Proxima Centauri star in a binary system, stellar system. It has 2 elder brothers, Alpha Centauri A and Alpha Centauri B. This planet is orbiting around the the smallest star, Proxima Centauri. So imagine how the climate of these planets, how the day and the night of these planets are governed by light of the 3 stars. At the same time, we discover planets which has no parents. They are rogue planets. Most possibly, they were the member of a stellar family, but they were somehow detached during their immediately after their formation. They are moving alone, and they are young. That's why they are hot, sufficiently hot, so that we can directly image them, and we can see that they are actually planetary stars. At least 6 to 7 such type of rogue planet or planets without parents have been discovered so far. In future, many more is about to discover. Another outstanding we came to know, and that is about the diamond planet. Now, how diamond planet? Can there be a planet made of diamond? Can there be a planet surface will be made of diamond so that it will be reflecting in the galaxy in the inside? Now, how diamonds are formed? Diamonds are allotrope of carbon. So in the interior of the Earth, due to the high pressure and high temperature, the carbon form a particular specific lattice, and that becomes diamond. Now through volcanic effect, these diamonds come out from the interior of the planet. Now when the solar system was born, it was born out of the self-gravitational collapse of massive cloud. that initial cloud that has equal amount of, means almost half of the carbon than oxygen. Solar system is oxygen rich, and that's why we see most of the oxide in our planet, like silicate oxide, which makes our rock, like water, like carbon dioxide. These are plenty. But if the star forming cloud has equal amount of carbon and oxygen, then instead of oxide there will be more carbide, more carbon molecules, more carbon related compound. Now if the planet is, as a result, the star will be carbon rich. These are carbon rich stars. So its planets will also be carbon rich, because the planets are formed from the same material the star is formed. Now if this carbon star, it is very near to its star, and so its temperature is very high, then this carbon may convert into diamond. On the other hand, it is far away, but because of the tremendous pressure in the inside, its entire core can become a diamond. Now if this diamond star will be appropriate place where water can sustain it, if there is life, this type of planet, then this will be the owner of an entire diamond planet. But the only problem will be there who delivered the planet to us. At the same time, we discovered planet which has no reflectivity, completely, means almost dark. Do not know so far that what type of materials it consists of. This is very near to the star, but its reflectivity is very less. So, its albedo, which define the reflectivity, is so less that it's a very faint object. It was discovered by indirect method, but got its albedo and the reflectivity, and it still wonder us that what type of material made this planet so dark. Now you see that here another planet which is so near, and so this is the hottest planet in our galaxy so far. It is so near to a star. The star itself is brighter than our sun, a few brighter than our sun, and the planet is so near that it is spreading its mass towards the star, and as a result it becomes a oblate shape, just like a rugby ball shape. So it is deviated heavily from electricity. Now these all planets are, these all image are artist rendition. They are all reflected planets. They are all detected indirectly. But at the same time, the astronomer has imaged some of the planets, and you can see this is a system. It's called 33b, where the 4 planet has been imaged, covered by an instrument called coronagraph. Now these, the star system itself is very young. They are less than 100 million years old. So therefore the planets are still collapsing. As a consequence, they are emitting copious of energy radiation that comes through the conversion of gravitational potential energy. And so they are very bright in the infrared. So this picture has been taken in infrared, Spitzer Space Telescope, and you can see 1, 2, 3, 4 planets, the real image of planets outside the solar system. So the problem is here, where I have started by telling that this is a search for exoplanets, but where is life, if life exists elsewhere? So far what I have told you, variety of planets that we have discovered in our, to get a viable answer of that question. So I will move to that question, to where is those planets where life exists, where life will. Now where to search for that? So actually we can search habitable planet, planetary system around any star, but in a particular position around that star, and that position is called the habitable zone, the circumstellar habitable zone. So this is a region around a star where the temperature will be appropriate for water to exist in liquid state. So that is called the habitable. This habitability depends on various conditions. First of all, the energy of the star or the brightness of the star, accordingly the distance moves around. So this is the sun, this is our sun, and you can see that the earth is in the middle of the habitable zone. It's also determined from the reflectivity of the planet and from the composition of the atmosphere that determines the effect. I'm not details of that. So the search, the focus shifted finding out planets in the habitable zone of the sun. Among all the planets detected, we found a planet in the habitable zone of a star. This is given Kepler 22, around the star Kepler 22. It is in a region of the star where water can exist in the liquid state. But then it found, it was determined that the planet is actually much larger than the Earth, so it cannot be a rocky planet. It will be very similar to Neptune. So it is a gaseous planet. Therefore, even if water exists, it liquid water on its surface, because the surface is doesn't have a rocky place to keep the water. Now, at the same time, Kepler discovered Kepler 20, where these two planets, Kepler 20e and Kepler, are just like Earth in size and also in mass, and therefore it is inferred that these are the rocky planets. But unfortunately, these two rocky planets were very near to their star, and so therefore their temperature is 1400 degree Fahrenheit and is 800 degree Fahrenheit, and they are so hot that they are really and if not Earth. So Earth continues. So the two conditions that we needed, that determined, is a rocky planet in a circumstellar zone where temperature will be appropriate for water to exist in liquid state. So Kepler and many other telescopes, they have discovered a few such type of planets which are rocky and which are in the habitable zone. But the question is now, is it sufficient? This is rocky and they have appropriate temperature, or they are in the habitable zone. Is it sufficient for origin and for the supporting or for protecting life? Or what are the conditions for life to really habitate in a planet? So then you move into a more fundamental question: what is life? Now the problem is that there is no definition of life, because life is. So what is the definition there? Suppose 100 years ago somebody asked what is water, described it. No, water is a liquid, it is colorless, it is odorless, it goes from up to down. But then somebody will bring a beaker of ethyl alcohol or methyl alcohol and tell that, look, this is also liquid. It doesn't have color, it doesn't have odor, it also falls to bottom. So how we will distinguish between two? So the description doesn't tell exactly a substance or a process. But now, today, if somebody asks you what is water, you immediately will tell that, oh, water is a molecule made of hydrogen atom and one oxygen atom. So it has a chemical formula, H2O. Now from chemical formula, fundamental formula, you derive all the properties of water. Unfortunately, such type of formula for life doesn't exist. So NASA gives us, the astronomer who for habitable planet, a working definition for life. And that life is a self-sustaining chemical system which is capable of Darwinian evolution. Now this is very small. immediately the biologist will start jumping. This cannot say anything. Of course, it cannot say anything, and moreover, this is a description, and a description is always incomplete and controversial. Now, if you slightly, then what we will tell, we can tell that life is an ensemble of organic materials. Organic materials mean the material which are carbon-based and which has oxygen and hydrogen as its partner, the carbon, and governed by self-sustaining synchronized system of chemical processes, that's the enzyme, and characterized by metabolism that makes the growth of the species, the replication through which a cell imitate or produce an exact copy of the cell, and the evolution through natural selection. Now, the evolution of natural selection is very important. Otherwise, when if you see one cat or one dog in Mars, you can say, you can tell that because of this evolution, tell that there definitely must be many cat and dog. Otherwise, those cat and dog are transported to Mars by some other planet. Or if some extraterrestrial intelligence was watching Neil Armstrong and Edwin landing on the moon or walking on the moon, they could have told that, oh, moon life exists in moon. But it is the evolution of natural selection that tells you that the life, it evolves from the simplest form to the complicated form. This is a role played by the gene. So I'm not a biologist, but this has given a new subject in this field, astrobiology. So what is this evolution? It is actually a minor mistake by a gene, but a systematic minor mistake by the gene. The gene which carries the information of the species in the cells, it exactly replicates a cell. But if it makes a little mistake, now how it makes? Suppose he has, the first person, he has a book, and he has a book which he has only one copy in the entire college. There was no photocopier, there was no camera, there was no Xerox copy. He did that, he just manually wrote all books. And while doing so, he replaces a few from the book and then passed it, his copy, to the next person. The next person didn't know about the original copy. So he also copied from his copy, and while doing so, he also replaced a few words and then passed his copy to the next person. And this process continues. Now, when the last version of the book will the entire book has changed. Now, if this book has many meaning, it will survive or be thrown out. So the gene, to adapt to the environment, it makes very slow and systematic deviation from its replication, and that gives rise to evolution. If the genes make very rapid without any system, then we call it cancer. So now the thing is that, another question, we do not know that what is the origin of life on Earth. A few decades ago, Urey and they showed that the necessary organic materials was synthesized from the inorganic materials. But then it turned out that the amino acid that he from the inorganic material is not used by the life there. There are many more amino acid, only few particular amino acid, like 3 amino acid guanine, those are used by life. Still, the question was there that if organic material can be on the earth itself out of the inorganic material, then can life be synthesized also out of those organic material on earth itself? This was believed for a long time, for decades, but recent time we have got evidences from asteroids that they carry organic materials, and they carry also some those amino acids. So therefore, it again question that whether this organic material which are the building block of life. It was not necessarily synthesized on Earth, must have imported from outside. If that is the case, then is it, can we just rule out that life was also at least in its nascent form, was not imported from outside to the planet, and then it got very appropriate to survive and to evolve? We do not know. So unless and until we can produce artificial life in our laboratory, we just cannot say that where life was originated on Earth or it has come out from outside. Even if we discover life outside the planet, then also we can tell that the life is a general phenomena, at least in our galaxy. And it may be imported to a place, it has appropriate condition. And now, what are these appropriate conditions? What has made life on Earth, whether it is originated on Earth or it has been imported outside from outside, how it has survived? You will be surprised to know that there is a rare combination, a coincidence of a combination and astrological condition that made life to survive on this planet. Now you see, first of all, the giant planets. We know that the system has a particular configuration. Here, the giant planets are outside of and the rocky planets, the small planets including Earth, are inside. Now here, outside where the Pluto lives, outside the Neptunian, there is a belt type of region called Kuiper belt. So these are the leftover material, consist of the leftover of the material which was during the formation of this planet. So what happened, the density was so low that this small ice and rock, they could not combine gravitationally, and so they have a very small, they could not form a planet, and they just orbit the sun in small pieces. Now, big asteroid and the short planets, they are the origin, the birthplace. This Kuiper belt is the birthplace of these comets and asteroids. Now, they always comes towards the sun. But because of the gravitational attraction of Jupiter, Saturn, Uranus, most of these comets either hit and get absorbed by the Jupiter or their path get deviates, so that they cannot come, many of them cannot come towards the Earth. As a consequence, the probability of the collision of comet and asteroid has reduced substantially. In fact, it is believed that 60 million years the Earth huge collision with a comet, and because of that the dinosaurs and the other larger species was completely extinct. Actually the Earth, the extinction several times, at least 5-6 times, when the entire land or even the water-based life was completely extinct, and again life formed, again it evolved. Now, most of the planetary systems so far we have seen discovered outside. Here the giant planets are very near to the star, and we have not yet discovered the rocky planet which are outside that. But in that situation, you imagine that will increase the frequency of the planets and it will destroy the entire planet itself. So the configuration of solar system is supporting on Earth. Next come the terrestrial magnetic. No, Earth has a magnetic field. This has been used for navigation for centuries. Now the sun, it emits energy particle, charged particle, and if the magnetic field was not there, the charged particle would have entered the atmosphere. It would ionize the gas, the molecules, and it would have changed the entire atmospheric composition in a irreversible way. Not only that, it could hit our body and completely damage the cells. But because of the presence of this magnetic field, this charged particle cannot enter to the atmosphere. It can enter only through the open magnetic field line This is because of the Lorentz force. It cannot enter to the closed field line, but it enters to the open field line, giving rise to the spectacular aurora, polar region. Similarly, the volcanoes and earth. You always heard that volcanoes and earthquake has a destructive effect, but you will be surprised to know that how these volcanoes and earthquake actually protecting life for billions of years. Because the carbon dioxide, which plays a double role in maintaining the temperature of the earth. The carbon dioxide plays reflecting agent to send back 30% of the starlight to the outer space, and that's determined the albedo or the reflectivity of the earth. Thus, carbon dioxide plays a role in cooling down Earth's atmosphere. At the same time, the stellar light that it hits the surface, the rock, it warms up, and the photon become the radiation become weaker. But while it is going away from the atmosphere, it cannot go so because it gets scattered with the carbon dioxide, water, and other molecules. It gets so many times scattered, multiply scattered, that it cannot escape to the space. It just gets trapped into the atmosphere, and thus warming up atmosphere of the planet. And that's what we call greenhouse effect. If we consider only the stellar light, the temperature of the Earth, Jupiter, Mars, all will be habitable. They will lie between 15 degree to 20 degree. But because of the reflectivity, the Earth reflects 30% of its of the sunlight to the space. The temperature should have reduced to minus 15 degree Celsius. The temperature of the Mars would have been reduced even far below, because it has also albedo of 0.2 or 20% of the starlight goes out of the space. And Venus, it has a huge 70% of the starlight it reflects out. So it could have been much cooler. But because of this greenhouse effect, the temperature rises minus 15 degree to mean 15 degrees Celsius. That has given that has the Earth to be habitable. Or if this carbon dioxide, the amount of the carbon dioxide changes, then this process will cease to act. Either Earth will become cooler or it will become hotter. Now carbon dioxide mix up with the rainwater and then produces carbonic acid, which is but it falls on the rock and it mixes up with the rock, which is made of silicon, and gives us oxide. Now, if this process continues, that within 10 years, all the carbon dioxide present in the atmosphere would have been completely gone, and the Earth atmosphere would have been changed. Because of volcano and earthquake, this carbon, which was combined with the silicon, again released out, and it comes out again, and within 1 million years, it forms a carbon-silicon chain, so that it goes mixed up with the silicon through the volcano and the plate tectonic or earthquake. It come out and it makes the balance the amount of carbon dioxide. At the same time, earthquake or plate tectonic and volcano that resynthesize the minerals in Earth surface or in the Earth atmosphere also. There is no volatility or plate tectonic, and the atmospheric material or the mineral in Mars is as old as the time of their formation. It has recycled or resynthesized. Venus' story is completely different. It has a very thick atmosphere which given a runaway greenhouse effect that made the temperature of Venus' atmosphere as high as 400 degrees Celsius, and that's why although Venus is the nearest planet in the solar system, it is the hottest planet in the solar system. So these volcanoes and earthquake plays an important role in protecting life on Earth. The next, the Earth, it is orbiting, it is slightly tilted rotation axis, and because of this tilt, which is 23.4 degrees, That's why we see the climate. That's why we see the rainy season, because of this angle. Now, because of this tilt, there is a precision. There is a rotation in the axis. Now, at the same time, tilt angle, this also changes. This also varies with time. And then the orbit around the sun, that also varies. All this together give rise to a cycle called Milankovitch cycle. Now you can see that in 24,000 years, the tilt angle make a complete precision. At the same time, 41,000 years ago. So the thing is that these dynamical changes, this dynamical perturbation is very small, so that we don't understand there is, not a substantial change, or there is no significant change in the climate of the Earth over a large time period. So why this is happening? Why this is? Who is responsible for this small the dynamics of the Earth orbits? Surprised to know that our moon, our Chandrama, is helping us in protecting our atmosphere. So we have a massive moon. When the Earth was formed, it was orbiting with a very high velocity. One day was equivalent to almost 10 hours. Then a Mars-sized object called Theia, that collided with the Earth. And the collision was so strong that Earth almost destroyed, but somehow it managed. It was in its very early stage, just 200 million years after this collision happened. And out of this collision, whatever has gone out of the collision, that is orbiting the Earth, and that is our moon. So with this collision, subsequently with its gravitational effect, it has slowed down the orbital rotation, the period of, not orbital, the rotation period of the Earth, and that has stabilized the atmosphere of the Earth. That if moon was not there, this angle would have been very much chaotic because of the gravitational force of Jupiter, Saturn, and Uranus. The moon is acting as a frame for tug of war, Jupiter, Saturn, and Uranus, keeping this tilt angle very small. If moon was not there, tilt angle will be very high, and the climate would have been very drastic. In fact, in Mars, there is no massive moon. There is two satellites called Deimos and Phobos, which are supposed to be some asteroid, small asteroid that has come with captured by Mars. So Mars's tilt angle is very chaotic, and therefore Mars's climate is also very chaotic, and it is uninhabitable. But our moon is protecting us from this. Now, this type of thing we cannot know that how to, because we cannot planet. Actually, what is the environment of this planet? So, what the astronomers is now doing to find out this life, they biosignature from the planet. That if there is a signature of light, reflected light of the planet. Now, what could be those biosignature? So, one is, methane. Methane can be produced by the degradation of biomass, or when living mass is, then it causes methane. But methane can be formed also through chemical processes. Certain thing is oxygen molecule. Now, at the early stage of the Earth, oxygen molecule was not available. There was no free oxygen. All the oxygen was chemically combined with carbon and other material with hydrogen, and they formed the oxygen. There was no free oxygen molecule. The oxygen started producing by a bacteria, cyanobacteria. Life came before that. Even when there was no oxygen, there was aniso-oxygen life. But then the cyanobacteria, they started photosynthesis. They emitted a copious amount of oxygen molecule. The entire environment of the Earth got changed. The species which found oxygen poisonous, they all extinct, and the species which found oxygen molecules, they only survive. Now these oxygen molecules can serve, but it is in the deeper region, can serve as a biosignature. Now these oxygen molecules in the upper atmosphere, when they hit by the intense solar ultraviolet ray, they get dissociated into oxygen atom. This oxygen atom and the oxygen molecule that combines to give rise the ozone molecule O3, which forms a protection shield to Earth atmosphere. So if ozone layer was not there, the strong ultraviolet rays from the sun would have penetrated the Earth atmosphere. It could have dissociated the molecules in the atmosphere. Not only that, it could have put huge mutation in life, in living, immediately cancer, and life could have been completely extinct. At least in the ground-based life could have almost extinct. So ozone. So what is happening that not only the planet is supporting the light itself is also supporting for the survival. Now this ozone O3, the line, you can see that this spectrum is taken from the Space Telescope Spitzer. This is Venus, this is Earth, and this is Mars. So you can see carbon. The ozone is there only in Earth where life exists, we all know. So our next strategy will be to find out the signature like ozone, methane, oxygen molecule. But the present we do not have to find out the spectrum of a planet, but fortunately, because of this subject has become so much acceptance from people like you, people are so much curious to find out if it exists or not. In future, several multinational project that is coming up, and you can see that Hubble, Spitzer, Kepler, this is NASA project, has already served tremendously. Hubble is still working. Spitzer gun test has been launched just few years. They have already detected a few planets, and it will be also detecting planets like Kepler did it. Then James Webb Space Telescope, which is a 6-meter class space telescope. The Hubble Space Telescope has this mirror whose diameter is 2 meters. The Kepler Space which has a mirror, the diameter was 1 meter. Now JWSSB is a telescope where the diameter of the mirror is 6 meters. So we can penetrate deeper into the universe. We can see much light from a much fainter object we can detect, and we hope many in habitable zone of around sun type of star can be detected by W. Now, yes, European has also some program. Gaia has already launched, Korat has already launched, everything. In the ground base also, we are not behind. There will be several next generation ground based telescope. In fact, India is part of the telescope along with Japan, China, and Japan, China, USA, and Canada. There will be extra large telescope, there will be giant Magellanic Cloud. So, the exciting thing. Now, so this is the case. Let us just see that our home looks like from. So we have seen that how we are searching. Now here is the planet. Here we are sitting, we are talking. This is taken spacecraft Juno, which is already reached Jupiter and taking picture. The next is from 1.4 billion years ago. This is taken from Cassini spacescope, which orbited Saturn. Here you see our planet Earth. Now, this is taken by Voyager, which was believed to have left even solar system. It was taken 6 billion kilometers away from by Voyager 1. This was sent in 1977. So you can see that while searching for planet outside the solar system, while searching for life outside the solar system, we have found that Earth is a very, very rare planet where all the necessary conditions were satisfied due to a huge coincidence, and it is very unlikely that there will be several such type of planet in the world. there are potential dangers also for the Earth. The collision by a asteroid may destroy it. So a supernova explosion may destroy the atmosphere. A gamma ray burst in our galaxy can also destroy completely the Earth, and a giant flare from the sun. The possibility of these effects are very rare. When there is no reason that why sun will behave like that. There is no star nearby known star and may go into supernova explosion. But in the terrestrial, there could be a super earthquake, there could be a super tsunami or volcanoes. Those are also rare. So the threat comes from man-made disasters, the change in environment, the increase in carbon dioxide. Even if there is a nuclear war take place, the atmosphere finished, will damage irreversibly. And so finally we come to why the Nobel Prize was given to Pegasi, because this discovery of 51 Pegasi confirms that the stars other than sun too have planets. The discovery initiated world search for exoplanet, and the subsequent discoveries of a wide variety of planets revolutionized our knowledge and understanding of planetary system. The discovery rekindled the curiosity of mankind. Is anybody out there? And hence, it search for habitable planet. At the same time, the search for Earth convinces us how rare is our own Earth and life on it. Gives us a lesson that the responsibility and duty of each and every citizen to protect this rarest of the rare planet, so that generations to come can keep on smiling.
Thank you very much, Dr. Sujan Sengupta, for the excellent talk. Unfortunately, we have to limit the question or the discussions because the hall has to be readied for another meeting. But both Sriram and Sujan will be available. Shall we meet outside? Okay, those students, people who want to ask questions, okay, outside we can meet, and there will be a question and answer session, and they will like to talk to the students, and particularly those who want to ask questions. I'm sure a lot of questions will be there. Sorry for this slight confusion in the program, because we have to hand over the hall to the next meeting, which is supposed to start at 6 o'clock.